This talk is about discussing how to identify problematic inter-domain routing issues, and this is joint work with Anja Feldmann, and we are with the Saarland University in Germany. So it is not difficult to notice that BGP is of great interest. There's a lot of concern about future scalability, open questions regarding convergence times, interaction with different protocols, and these kinds of questions need answers. And our first step towards a better understanding of BGP is by trying to identify what is happening at the moment and what causes this. But instead of just presenting you some results of our work, I would like to introduce you to the tool we've used for deriving these results. And this tool is called Character, and it helps answering questions about BGP. So please let me try to give you a short overview of the tool. It operates mainly on two levels. The first level takes care of the processing of the raw data and all low-level details. So it provides you with an intermediate abstraction level, and on this abstraction basis you can then develop useful functions for the classification and characterization of BGP updates. So this is exactly how the tool works. You collect your raw data from your routers with tools like Zebra, MRTD, just among others. And then our file finder package provides you with this intermediate level for the automatic classification between and within the different peering points. So you just state the time period and the peering points you wish to be analyzed, and that's all. The function for the classification is provided to the file finder module as a parameter. So you may write your own functions, or you use already written functions that come along with our check package. So in the remainder of the talk, I would like to introduce you to one function we've called route change events, and this function tries to identify different kinds of changes like flapping, session reset, update bursts, and so on. So the characterization is of course done by processing all of the updates. There are two different interesting contexts in which you can view an update. First, of course, all updates for the same prefix, but there's also an interesting context in which you can view updates, all the updates that appear within a short time period. So our function works in the following way. It takes two surrounding table dumps as an input, and we start with the first table dump as a reference for all the updates. Then we process the updates and classifies them according to some rules and concepts which I will explain later. And then we try to rebuild the second table, and this is done to identify missing updates and so verifies your raw data. So that's the input. What's about the output? We show in the output each update in one line and append our characterization to the end of the line. So this looks a little bit like Merritt's route btoa output, but with one big difference. Our output is first sorted by the prefix and then by time. So in this example, we have two updates here, the 80.96.50/24 and the first two updates for the 80.96.150/24. So let's look at the data where this example is derived from. So we used our tool to characterize the updates for 1 week. We take the data set was collected and published about 3 weeks ago from the RIPES RISC project, and you all know these kinds of plots. We show on the x-axis this 1 week in mid-January, and on the y-axis the number of updates during 2-hour bins. Different colors means different peers, and so on. You see more and less intense time periods. And what is noticeable here is this very large spike on the left side of the graph that is due to a collection point failure. And after the session re-established, each peer sends about 107,000 updates to the collection point. So that's a very large spike on the left side. So that's just the overview of our data. as I just mentioned, the output is appended to the end of each line, so this results in very long lines, and this didn't fit on any slide, so we splitted them for the presentation into pieces. So we start with very simple classifications, just by counting the number of each update, the time to the previous prefix. We print the classification which Craig Labovitz et al. Introduces with its AA-dubs and AA-diffs, and then a more detailed explanation of what exactly has changed. Is the AS path affected? Has the actual path through the ASs changed, or is just one AS repeating its own AS number several times? The first we call a AS path weight change, and the second we call a policy change. So is the AS path getting longer or shorter, or does the number of ASs stay the same, like in this example? What else has changed? The community string is, in this example, has been changed, and of course, if the origin attribute would have been changed, we would have been written the word origin here as well. So this is a little bit too much information to visualize. So for the visualization, we group them into three classes. First, the AS path changes. The second class is a policy change, which means that one AS is repeating its own AS number more or less often. And the third class are all other attribute changes. So three classes results in 8 possible categories where an update might fall in. So an update might have only changes to the AS path, nothing else, or it might have changes to the AS path as well, but also a policy change, or it falls in all 3 categories, and so on. So this plot is again for our 1-week time period. This is a relative plot, which means we take the percentage of updates falling in this or that category and plot them in an additive fashion. So the result must be all the time 100%. This is indicated by the yellow line. I think it's a little bit difficult to see the yellow line at 100%, but believe me, there is a yellow line right at 100%. So you can interpret the distance, for example, between the light blue line that is slightly under 50% and the pink line as the amount of updates, as the percentage of updates that arrive with only an attribute change, which is in this example roughly about 25%. So you see here again our collection point failure, which falls completely in the yellow category, and this is quite obvious because we use the tables as referring, as references, and then we have the failure and get all the updates re-announced. So we have duplicated announcements of the tables, which means that nothing has changed. So what else is interesting is that from the bottom to the green line, which is also slightly under 50%, are all changes due to AS path changes. So the output of our tools looks in this a little bit more in details, but I don't have the time here to go into details. So next, the output of our tool will print the old AS path, because the new AS path is providing the connectivity. That means that the old AS path somehow has lost the connectivity. So it's printed as AS numbers, but also we show the percentage of prefixes that are still associated with an AS versus the total number of prefixes that might be associated with this AS. So if an AS is losing its connectivity, of course from the collection point of view, this results in very low percentages here and are marked with an asterisk. So this were only the changes between the consecutive updates. Let's look at updates with equal attributes. So if you see a set of attributes for the first time, we call this a new change. If there are 2 consecutive updates with equal attributes, these are duplicated changes. If the first and the third update are the same, the third would be called a flapping change. And if the first and the fourth have equal attributes, this would be called a reconvergent change according to the classical case, where you have your best path, that's number 1, that's maybe stable in the table. And then you have a withdraw, that's number 2, because of a failure or something like that. And this withdraw is replaced by an alternative route, that's number 3. And after the reparation of the failure, the best path gets available again, so that's number 4. And so number 1 and number 4 have equal sets of attributes, and so number 4 would be called a reconvergent change. So the output of our tool reflects this by calculating the distance to the last equal update. So a distance of 2 means a flapping, a distance of 3 a reconvergent change, and so on. So next we print the number of updates where this first occurs. So a 0 in this case means that this set of attributes occurs for the first time in the table, and so on. We have more information about flapping and reconvergent change there, but let's look at some nice plots. This is again a relative plot over the time. The black line indicates the introduction of new attributes, which is in this case about 21% as a mean. Don't get confused with new prefixes that are introduced, which is of course less than 1%. I think in this example it was 0.4% or something like that. So this is the introduction of new attributes. So we don't have very much duplicated updates, but except for our collection point of failure. And we have a lot of flapping. That's the distance between the blue and the red line, and so on. The trend towards the smaller number of new changes is quite obviously because at the end of the week, more information is of course known to the system. So it is remarkable that there are still such an amount of new updates that are introduced to the system. So next we look at the interarrival times for the various kinds of updates. This plot here shows the density distribution of the logarithm of the interarrival times between equal updates. Using the logarithm of the interarrival times, let us still see something on the x-axis and still be able to compare the areas. So two areas of the same size here corresponds to the same probability. So as I just told you, on the x-axis we have the number of seconds logarithmically scaled between equal sets of attributes, and on the y-axis the probability. So as you can see, most of the re-updating with same attributes happens within 15 minutes. Let's see if I can get a hand here. Between 15 minutes and maybe still to 1 hour. But for the flapping and the greater distances, this drops significantly at the end of the curve. So let's look a little bit into possible causes for this. For example, session resets. It is known that session resets have a deep impact on BGP. The solutions to the problem are already proposed, like in the IETF draft on graceful restart mechanism on BGP and so on. So we like to show you a possible identification method for identifying session resets. So our tool analyzes all ASs that are involved in an update. These are the ASs from the new AS path and the ASs from the old AS path. And for each AS, we calculate the fraction of the routing table which is updated recently. So this means for each AS, we keep track of which prefixes are associated with with an AS from our collection point of view, of course, and then we count for a 6-minute window how many of these prefixes have been updated. So the resulting percentage turned out to be a good heuristic for identifying session resets, and this is something like the validation for that. This is again a density plot. On the x-axis, we have the fraction of the prefixes associated with an AS which have been recently updated, and on the y-axis the probability. So in this case we distinguish between originating ASs and transiting ASs. So an originating AS is just the last AS on the path in our definition now. So in addition to our write data, we have here also data available from a local German ISP. So for the originating ASs, there's a nice peak right over the 100% with the green and the blue lines. And this peak shows a significantly higher probability for an originating AS to exchange their whole routing table and accept for example, then 40% or so. And we would consider these updates in this peak as being part of a possible session reset. So for transiting ASs, we don't have this very nice peak there, but on the other hand, we don't expect that transiting ASs exchange their full routing table that are associated, the full associated routing table, because of the much higher connectivity of transiting ASs. So I can explain after the talk to you how we managed this, but it works also very good. So the output of our tool don't only mark these with an asterisk, but also print the number of ASs that are involved in a session reset and blames these ASs by printing their AS numbers. So the next question you are probably asking for is, how big is the problem? So this is again a relatively plot over our time period. Beneath the red line is the percentage of updates that are marked as being part of a possible session reset, and above until the blue line are the rest of the updates. I think I don't have to comment this anymore. So further classifications include a rate of updates in seconds, and if this rate exceeds some certain threshold, it's being marked as one of these little peaks there. And so that's it for our current classification. We really would like to hear from you what else might be interesting or necessary, so please drop us an email. And in the last few minutes, I would like to go one step further and analyze the bursty behavior of the updates. So when a route changes or a change to the infrastructure is done, not just one single update is created, but rather there are several update bursts are generated. So if a peer sends 2 or more updates for the same prefix within a short time period, we would consider these updates as being part of the same update bursts. So like someone is grouping packets into flows, we are grouping updates in this way together. So we can now look at the characteristics of such update bursts. And for example, the duration of these update bursts. This is a density plot, again logarithmically scaled, of the duration of the update bursts on the x-axis and on the y-axis probability. So the blue and the red line are for our write peers and show the duration with 2 different timeout values, 15 minutes and 1 hour. The green and orange lines mark our local German ISP. And as you can see, the curves are mainly similar, except for the values between 30 minutes and roughly about 2 hours. And there the curves with a timeout value of 1 hour show much more effect. And these are due to route flap dampening, of course, which you can't see with a 15-minute timeout value, but which you get with a 1 hour timeout. So about how many updates we are talking about. This plot shows the number of updates per burst, and that's the interesting case. It's again logarithmically scaled. So the blue and the green line indicate all updates from our right here and our local German ISP, and the red and the orange line indicate new changes. That means updates with a unique set of attributes. So as you can see, most of the bursts contain only a few updates, up to 10, but some bursts can contain more than 10,000 updates, and some have more than 1,000 different updates. So, in summary, our tool tries to identify the structure behind the updates by some classification. It provides statistical information and identifies missing updates for the verification of the raw data. So what our current research interest is we like to use these characteristics we've found so far in the real net and build a workload generator for BGP, not just any one that is announcing some flapping routes, but rather one that is capable to test the scalability of routers and of BGP with realistic traffic characteristics. So this is necessary to benchmark the performance of routers and to test for their limitations. So that's it. Thank you very much for listening. Do you have any questions?